Hello, Jeff Disher here again. Today I'm going to talk about something which was requested, which is the ARM architecture. Now, first of all, what am I referring to when I mention this? Well, something that you might not realize is you probably already have an ARM processor in a device that you carry all the time, your cell phone. Almost all of the smartphones in the world run on ARM architectures. Now, the thing to remember here is ARM is not a company that makes CPUs. They make specifications for the CPU and then they license it to people to manufacture them. This is why, for example, you might have an iPad which has an Apple A4 or whatever they're calling it, which is an ARM processor that Apple bought a license from ARM and then built themselves, so that's why it behaves differently than some other architectures. While a Samsung, you might have a phone with like a Samsung Exynos 5 or something, which is going to be a architecture that it's an ARM license they got from ARM, and then they did some of the things they wanted to it to make it customized for their purposes. So you see this a lot. But the key thing to remember is that they're, for the most part, all the same thing. There are differences between some of the actual specifications for ARM, but for the most part, we kind of all refer to them as the ARM architecture. Now, ARM itself did not actually start out this way, building cell phones and CPU specifications. They were actually originally building CPUs and computers for something called the Acorn RISC machine. Now, this was back in 1985 in Britain. The company is still based in Britain, but they don't actually make these computers anymore. How this goes is the ARM32. This was kind of the instruction set used by the vast majority of these machines. This was created back when they were originally starting, and it's kind of based around all the same assumptions that a lot of RISC processors around that time, kind of the late 80s, early 90s, were making. Things like MIPS and PowerPC and ARM, all these instruction sets, they kind of had some similar ideas behind them. And so first of all, ARM32 itself has a fixed width instruction. Every instruction is 32 bits wide. And this is something which is common with, say, a PowerPC, which also has 32-bit instructions, but different from, say, an x86, which has variable length instructions. So this is good because it means that you can do really fast decoding of a long sequence of instructions without very much hardware, like without very much actual silicon, because you know where they all start. But it means that things are much more spread out. It takes a lot more memory for you to store an instruction that, maybe you use this instruction a lot, and it takes as much space as one you never use. So that's kind of the trade-off that they had with that. And specifically in the case of ARM32, they also have 16 general purpose registers, all 32 bits wide. Now this includes things like the program counter and the stack pointer and other special registers. So this is kind of common with CPUs of that era they're starting to try and add more registers themselves, but again, mid-80s, you're still not going more than 16 without incurring a huge cost. And a really interesting thing they added with the ARM, which you don't see it in very many architectures. I believe the only other one that had it that I'm aware of is the Itanium, which is something called a predicate. Now what this means is that normally you'd say when you're building writing a piece of software, you're going to have some decision making that you have to do. So it's going to be internally like, if name is Jeff, then owner is give keys to house or something, and otherwise reject keys, right? And so you're going to have this kind of if-else system. Now this is common in software, but also it's how the CPUs would work too. They'd actually have to say, okay, execute this, now figure out what the result was, and based on that, jump to one of these places where we're putting these other instructions. Now this is kind of a problem because it causes what's called a branching penalty, which means that in order for it to know where to jump to, it has to finish figuring this out. It can't just do the next thing. So predicates actually allowed you a way around this. You could do interesting things like say, okay, if name is Jeff, then, and you just kind of solve that, but then also just continue and go on to say, give keys to house if it's true, and reject keys to house if it's false. So it would actually run all of these instructions one after another and could actually decide internally, okay, we're only going to actually write back the instruction, which means to complete executing it, if the predicate is true. And so this means that the result of the predicate is available at the end of the instruction instead of at the beginning. So it solved a problem of how you'd actually solve the branching issues that you'd normally run into in software. So this is it was a really clever idea, and there's a lot you can do with it. Now, there were some other things that, as they went on, this was fine, all these things worked. Now they started to run into problems where, as they moved more into a company that was building licenses for the architecture, they were really moving into areas of low power computing. So a lot of things like embedded systems, and these very kind of simple things that don't have very much power. They need to run very effectively and efficiently for a long time, and they don't have, like, they're built to be kind of low power or cheap or something like that. So often they'd end up kind of resource constrained in certain ways. One of those is, okay, you're having to read these 32-bit instructions. Well, maybe the memory bus on the system we're building can't read 32 bits at a time. So now it's going to take multiple cycles just to get the instruction to execute. So this would be a huge problem because it would just slow things down a lot. And again, when they were looking at it, they realized, wait, there aren't actually, like, there's a great number of programs which almost exclusively use a very small number of instructions that we have. So this is why in 1994 they came up with something called Thumb. Now this was a great idea because it allowed them to say, okay, we've got these great 32-bit instructions all over the place, but let's say we actually made a slightly different version of our instruction set, which was only 16 bits, and it wasn't as expressive. So maybe you need multiple instructions to do a simple thing, but that's not a very common thing. So okay, we'll create this, and we'll make sure that we kind of make these instructions nice and small so they can all fit tightly together. Now this was great because now it meant that to run one instruction you only need to read 16 bits. So some of these low power machines could actually run much more efficiently, much faster in these environments. I believe the Game Boy Advance took advantage of this. But you know, there's kind of a lot of possibilities that have gone on with that. Now, going forward, this continued to be kind of useful in various environments because, yeah, you get better code density. So now, okay, yeah, it might take a few more instructions, but most things don't, and now I don't have to, fetch all these instructions out of memory. Even on a high-powered system, that would be a benefit to have these things be smaller. But eventually, the trade-off in just having all these kind of auxiliary instructions being added in order to make sure you could actually do this quickly or to actually solve some of the problems you had was becoming a limiting factor. So it meant that thumb instructions were, it was generally kind of being viewed as a slower way of using an ARM processor. So something they created in 2003, and this is of course with modern realities where, or closer to modern realities, where we weren't getting as worried about the extra silicon it took to do instruction decoding and things like that, they created what was called Thumb 2. Now this was kind of a neat idea because what they did was they said, okay, it's going to be a combination of 16-bit and 32-bit instructions. So this way you can actually have the best of both worlds. You can have your really tight instruction code density when you need it, and you can also have the bigger 32-bit instructions when those are what you actually were wanting. So this kind of benefit led to this kind of solution to that trade-off problem led to some benefits that have been seen in performance. So if you're doing work on an ARM processor, it's worth looking into these. How does your workload actually compare between Thumb 2 and ARM32 on a given workload? Now, one of the other things that a lot of architectures have, which I haven't touched on yet, but is something which, of course, ARM also provides, much like them, is something called a SIMD unit. Now, SIMD, of course, means single instruction, multiple data. So it's one instruction operating on lots of different pieces of data. So it's doing the same thing multiple times, but just saying, can you do all this at once? Now, in the case of ARM, this is called Neon. But it works very similarly to what you're going to see on other architectures like, say, MMX or SSE or 3D Now on an x86, or Ultivic or VMX on a PowerPC. But pretty much every architecture has some notion of this. On ARM, it's called Neon. And there's, of course, lots of clever things they can do. But I'm not going to go too much into the details of how it's built. Something which was very, very recent, this was like 2011, this was announced, is they're actually going to create a 64-bit ARM now. And, well, they exist now, But this was a very recent announcement they were going to do this. So this is kind of interesting because some things were changed in ways which are relevant. Like, for example, instead of the 16 registers, all 32 bits wide, including your program counter and stack pointer, now they're going to do 31 registers, which are all 64 bits wide. And on top of that, you'll also have your other registers like program counter and things like that. So this, of course, is it's a similar transformation to what the x86 did, where not only did they make the registers wider, which was kind of the bare minimum you need to go to 64-bit, but they also added more of them. So this will mean that there's more possibilities for compiler optimizations going forward on ARM64. And it also kind of signals more of a move into some higher power capabilities, which might need more silicon to actually create, but nonetheless are useful. So you're starting to see these things show up in the wild, but again, for the most part, it's not that important because most of these systems, you're not running programs on most ARM devices that need more than 4 gigs of memory, which is one of the big reasons why people went to 64-bit. And this other change they made with adding the new registers, well, they're going from 16 to 31. It wasn't as big a jump as the x86 had, so the benefits there are going to be somewhat smaller. So there's less of a real imperative to get there now, but it is something that's there, and it is starting to show up, so it's kind of neat. Now, something that I wanted to end on, which is a really, really creative idea that they've been doing fairly recently in the ARM world, and we're actually starting to see some hardware which uses this, and it's kind of neat because it flies in the face of all the assumptions we made before in software, and that's something called big.LITTLE. Now, what is this? Well, historically, when you looked at how we had multiple CPUs in a system, we used what was called symmetric multiprocessing. We had multiple processors, and we said they were symmetric because we basically said there's nothing really special about any of them. They kind of all behave more or less the same way. There's some differences with how they access memory, maybe, but for the most part, we kind of say they're all equal citizens here. Now, as we went to multi-core, we just started, instead of having multiple actual processor packages, we just started shoving more cores onto the one package. And this was great, except that, there's some other limitations where that's going. But big.LITTLE is more like someone took this idea and said, okay, can we solve some other old problems with this? Like, what about power? Right? Power has always been something that ARM's been concerned with, and going to just add more and more cores usually increases the power consumption you're going to have, or at least your worst case power consumption. So they started saying, can we do something kind of weird here? Can we, instead of having 4 high power cores, what if we had maybe 4 high power cores and 4 low power cores? And so this is how big.LITTLE works. It's based on the idea that you have big processors, which are like your high power ones, and you have little processors, which are your kind of low power ones, the ones that are, they still are quite competent, but they're made to consume less energy. And so this, of course, is a neat idea, because yeah, there's lots of potential you can see here. But, well, where does this leave the software? Because it's always been based on the idea that these things are all the same. Now you're saying, no, now they're completely not the same. One processor core is not the same as another. So this led to a few different ways of trying to solve this problem, how to fit the square peg that is big.LITTLE into the round hole that is our old assumptions about symmetric multiprocessing. Right? How does your operating system kernel decide where your process should run? So there's some problems to solve there. So the 3 main solutions to this problem, the first one is what's called clustered switching. Now this is very easy because what it does is it essentially says, okay, you've got your 4 high power cores, your 4 low power cores. Let's just say that we're running either this machine or this machine. And depending on our power consumption needs at the time, we'll swap them. So the whole chip runs at once in either a high powered mode or a low powered mode. So you have these 4 high power, 4 low power cores, and the CPU, or the operating system acts as though you have 4 cores, whatever those might be at the time, depending on its power needs. So it essentially is like treating the whole chip like it has an ultra low power mode. So this was easy because it doesn't change anything. All the CPUs are still kind of the same relative to each other. It's just a new little option for going into a low power mode. This is okay, but it's really a lost opportunity. This doesn't really give us what we wanted, which was the ability to actually make these decisions on a much finer granularity and with a much more dynamic kind of capability. So this led to what was called in-kernel switcher, or of course, what everyone actually calls it is IKS. Now, this is where the operating system kernel itself now looks at these 4 high power and 4 low power cores, and instead of cutting them this way, it cuts them this way. And it says, okay, let's treat this like there's 4 CPUs that all independently have a low power mode. So it can switch each one in or out of this high power, low power behavior. So now it can determine per process, depending on what it's running on one of these cores, does it want to use the high power one or the low power one? And there's some complexity with how it does that, but it gives it that ability to make that decision. Now this is something which of course is where you start to see the changes in the assumptions. Now they're not all going to be the same. So some things have to change to account for that. But of course, there's still a missed opportunity here. Why are we talking about 4 cores? We just keep drawing 8 here, but we'll keep talking about only using 4. Well, that's where you get to the last one, and this is kind of the more ambitious approach to it, the actual solution for how you effectively use all of these resources to your advantage. And this is what we call heterogeneous multiprocessing, or of course, HMP. Now this is where things are going now. It's where we're trying to actually get the most we can out of this. In this case, the operating system looks at your big little core and says, 4 big cores, 4 little cores, okay, 8 cores, I can count. And now it has to actually determine where to put everything. Now this means it can actually run 8 things at a time if it wants to. None of the other solutions could do that. But it also means it has to figure out, okay, well, which one do I want you to run on right now? And how do I deal with problems like, I've got 8 things to run. How do I kind of rank them this way? And there's all kinds of complexity in terms of figuring out how you do that, how you adapt to much more tight power constraints. Maybe you want to shut off all your high power cores. Sometimes it only run in low power modes. There's lots of sort of interesting problems that this introduces, but they're neat, and there's a huge opportunity there because, yeah, not only do you now have more cores to work with, but you have this really interesting ability to adjust to your situation. So you can now go into really low power modes, maybe because your battery's low or something, and then you plug in your phone and all of a sudden all these extra cores come on and your processes start running a lot faster and you can now run more of them, things like that. So it's a really neat possibility, and we're starting to see this hardware come out fairly recently. Only in the past couple of years I haven't seen anyone doing much talking about it. So it's a neat opportunity, and I hope that we'll see something kind of interesting in the future there. So anyway, I hope that this talk was valuable. And again, like in all my talks in the past, if you have any questions, send me an email at jeff@jeffdisher.com or reply here. And of course, you can always trust me on Open Autonomy if you're using that system at this QR code. So thanks for watching, and I hope you enjoyed.